So last time we talked about the Kennedy Masaki transformation, and then to see the field T2 cross T2 symmetry. And then today we want to talk about how they play to the dimension. So H Heisenberg is something like that. Like this way, periodic boundary condition, H trivial, and the sum of J. Sorry. J boundary. And then we take the so both unique, so periodic boundary condition, then unique gap state, ground state, and then the correlation function. Exponential decay. Exponential decay. Sorry. This is not one. STP. And then H impact is smaller. And well, so this is the projection. So some students ask me about why they, so exactly, so we didn't show us the ground state, and there's some first excited state, there's a gap between the gap. We didn't for AKLT, we didn't show that this E gap explicitly, but one can show this the E gap, so which is kind of like, I mean, it's not that difficult, but so this one is already shown in the analysis is kind of involved, and then it's going to be boring to show this E gap. So rather than doing that, so we show that this is exponential decay by using a matrix product state. So if you're interested in the showing this the gap so derivation is this Kakatani. In section 7. So I wrote the exact section, but he showed that explicitly showing that there is a existence of gap 7.1. But if there's a gap in the first excited state, this means that the system has a typical energy scale. Yeah. Or this means that there is a typical length scale. Which I call it this So then the consequence is that the correlation function and the ground state Sj Sk E is the exponential decay over like this. So this is usual physical consequence of if you have a gap, the correlation function is exponential decay. On the other hand, gapless. So the people so using matrix products, say last time I showed this one by this people that asked me. So I call it the let's see, balance point state is sum of the trace of S sigma 1, S sigma L, sigma 1, sigma L, and this way. And here we assign distance of some student asking why this is. Like this thing. So A that here 2x2 matrix, 2x2 matrix, and then here you have the alpha 1, alpha 2. So here alpha 1, alpha 2. So this line can be understood as the matrix, the labeling with matrix entry of the matrix A. And the sigma 1 is the choice of spin. And then what we did is that we essentially computed the similar system and then here I put the S and then here I can wherever the S and then compute this partial function and then the last time I showed that this one is 1/3, I will say graph with the that's how we show it. So by explicitly showing the correlation function is explosionary decay, means that the typical energy scale in the system, which introduce gap in the system. That's one question. I wanted to, one point I wanted to emphasize. And then also, so gap left. So we know that this means the strict one half integer is 3 half. The system, hardware system gap left. And the correlation function is the roughly speaking this. So it becomes like this here. Log I minus J minus. So it's behave very different. So they behave. So the behave more like a power law. In this case, in 1 plus 1 dimensional example, it becomes more like a exponential. So sorry, log. So gapless means that the theory, a continuous level, constitutive continuous level. Then the theory becomes so-called a cohomology theory. So they behave very different. So that's what the Howland project says out of. And S equal to 1. And another thing we did is that so E2 plus E2 symmetry will show up for open in Chinese. So for AKLT, so you have balanced bond solid. Use balanced bond solid picture. Like this way. So the plus minus spin. This edge mode. Edge state will show. Edge state will show. So that is the freedom with D2 plus D. The spin up and spin down corresponding to D2. And if you take the and what we saw is that if you consider Heisenberg, H. Heisenberg, and you make that transformation, then it will become sorry, I think I told you something strange. So in the case of spin on top, it becomes like this way, according to Bayes. Sorry, I think that's okay. So this was derived by Bayes. But by Yang, so there's no energy scale up here, and it's just it becomes hollow. And last time when you applied Takasaki transformation, we obtained that the Hamiltonian is something like as follows: half of minus. Like this one. Okay. Sorry, it's opposite. And this Hamiltonian, so I'm not going to write down the Kennedy Takasaki again. I'm not going to write down. Because I already wrote down before. And this Hamiltonian, I call it H2, is that the has a D2 cross D2 symmetry, and then this can be understood as the rotation, I rotation in along x and y and z axis. So as I mentioned many times, so D2 cross D2 has no trivial element, so E, X, and Y, and Z, and X and Z, and then this symmetry. So the relation is x squared is y squared equal to z squared is equal to b, but xy is equal to yx equal to z, and if everything is equal. And so this is the so x, y, x, everything is equal. Equal means like this. So this is d2 plus d2. Okay. And then there was a question about the two contracting statements. So one thing I mentioned is that so because of this one, consequence of this D2 cross D2 symmetry, Hamiltonian has this symmetry, so that the four generate ground state. For ground state. But on the other hand, so Heidelberg spin change, I told you that there's a singlet, spin one singlet, and triplet. There's a gap. There's a small tiny gap, and after that there's a big gap. That is Halley gap. Yep. So even though there's a fourth state which is way lower than this above Halley scale, but there's a still gap. So there's a contradictory statement I made last time. And the truth is that this gap is in fact e to the minus L over the gap. So therefore, this is true when L goes to infinity. So if you take the number of sides in infinity, it just becomes. The reason is that, as I mentioned, so this they have the exponential. So if you have the edge mode, edge state here, and with side L, they still can interact with the exponential decay. Sj, C, Sj, Sk, C is e to the k minus k over C. So therefore, they can still interact. The edge mode can still interact, and it can create this small energy gap between singlet and triplet. And then this triplet often called this triplet. So I did this statement. Spin one half is a two-dimensional representation. So spin up, spin down. The two-dimensional representation, and it's decomposed triplet and then the singlet. And this triplet often called Kennedy triplet. So there's a contradictory statement I made, but this is a precise statement what's happening in this system. Okay, so that's one thing I wanted to review in the content of last time. And also, so the expression of this spontaneous symmetry breaking. So once you pick one of vacuum, one of ground state, then system has G2 plus B2 is spontaneously broken. So this is SF. So the question, what the meaning of this thing? So the typical example is Lagrangian to 1. So if you have a potential, so the Lagrangian has the whatever kinetic term or P squared. I don't like M. Okay, you have P x, and this Gx has a symmetry. Z2 symmetry. H of the minus x. So then potential can be like this way, so this Bx squared is x squared plus lambda x. So if lambda is positive, it becomes like this. But if lambda is negative, it becomes like this. Sorry. The opposite. Okay. Lambda is negative, it becomes like this. The potential side. So the potential becomes like this. And then there are two vacuums, which is related by x goes to minus x. And then, so this is really Ginsburg-Landau picture of the phase transition. Once you pick one of the vacuum, okay, this D2 symmetry is spontaneous, spontaneous broken. Because I mean, here there's a vacuum, but there's no vacuum here, so there's a symmetry broken. The same thing happens over here. Even though for degenerate ground state. Okay. And then, so if you just have the Hamiltonian, it's something like S, minus S, H trivial plus S, the work. Then, this E gap. So S is equal to 0 and 1. If we take numerical summation, we always tell you something like this. And then here it becomes gapless. So let's say star becomes gapless. And here it's called trivial phase. And here we have a Hausen phase. And then so if this transition is this here phase transition must occur if we impose HS to have C2 cross C2 symmetry. C2 cross C2. If you don't impose C2 cross C2, there's something strange can happen. So there's an X like this, right? X, Y, so it's a Z, and there's a space of Hamiltonian. And then here you have something like inside here, So xy plane D2 plus D2 is reserved, but z-axis z is non-zero z breaks. D2 plus D2 is broken. If it is broken, you can just move from one phase to the other phase by just taking z to belong trivial. But so this phase transition occurs only xy plane. So this circle is this gapless critical point. Critical point. So if you impose D2 plus D2, you must cross this circle. So this is just schematic diagram, which is the gapless critical point. But if you don't impose D2 plus D2, one can move one phase to the other. So the phase is protected by this D2 plus D2 thing. That's why it's called D2 plus D2 symmetry protected topological basis. But the phase is protected by symmetry. Okay. So that's what really happened. And today I want to discuss why it's called topological. So we know that it's a phase is protected by symmetry, and why it's called topological. To describe that, we need a notion of the so-called projective representation. I think I made. I need a particular file which I will transfer to the iPad successfully. Let me do that. Okay, so the notion of so projective representation. Projective representation. I don't know which one is better to go first. Okay, maybe let's do it this way. Okay, so let's consider the point given. So let me think about it. Okay. consider the following thing: how is equal to symmetry last time. So this matrix product state state which is sum over sigma. Okay. So let's try to see how it acts on it. Okay, so then so we can see that the point. So suppose high rotation along. Let's consider pi rotation along the axis. Let's consider such a thing. Then so the UZ x and j that is exponential minus pi I scj. So then this state UZ of j acts on sigma j state as follows: -1 to sigma j and then sigma j. Like this. Because I mean sigma j is plus minus 1 and 0. Okay? So that's what's going to happen. So recall that this Sj is something like 1, 0, minus 1. Okay? For example, if you plug that into here, you get this d rotation along a pi rotation along the axis will give you this. Okay? Now, so let's look at how this operation. Let's consider the current of. So if you do the pi rotation along g-axis, what you get is that like this acts on BPS state, and then this one is something like this one. Like this. Okay. But we can just transform. So each pi rotation around the d acts on each side, which will give you this state minus 1 to the top. So this can be rewritten as follows: sigma of x of a tilde sigma 1 a tilde sigma l minus 1 sigma 1 dot sigma l so where a tilde so this is a tilde sigma j is 1 minus 1 to sigma j and a sigma j. And we know that so a sigma is something like 1 over square root 1 0 0 1 a minus this over that 1 over square root 0 1 0 0 the 0 is 1 up 1 minus 1 0 0. And then So this one can be understood one. Sorry, this one can be understood. I don't remember normalization. Sorry, so sigma plus is 1/2 sigma x plus I sigma j. Sigma y is it correct? Correct. And 1/2 or square root 1/2. Okay. 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 So then this is square root 3. Looks like the 0 club. So like this. And then this one can be understood as the UC and sigma, and sigma UC, where UC is by E to the pi I S B sigma J J and minus I. I think this is correct. So this is in fact minus I e to the pi I over 2 sigma b. Sigma b. And this is minus I. Cosine pi I over 2 1 plus sin I. Oh, sorry. I think it's, I don't need a minus sign. Just a moment. It says definition. Oh, yeah. Minus. Then cosine pi over 2 times 1 plus minus I sine pi over 2 sigma c. Okay? Is that okay? And then this is 0, right? So therefore, this is minus I sigma c. So therefore, minus I 0 c. Is it too hot?
Moving.
Yeah. Cooling? Oh, wow. I don't know how to adjust. Anyway. I mean, if you want to avoid it, then you should go to or tunnel. And you can check this one. You can explicitly check this one. So okay. So this means that this. So if you look at this one, so for instance, let's check this one. So you see it's something like yeah, minus I sigma c times alpha sigma c times minus I sigma c like this one. You know what I mean? Then this will give you the minus of alpha sigma c, which is minus a. You can check like this. Yes. And you can check the same thing. You can do that. So So this is called projective reference. So this action is called projective action. Action of D2 plus D2. D2 plus D2. So as I mentioned, D2 plus D2, the great group is E, X, Y, E, that's X squared, Y squared, D squared is equal to E, X, Y, X equals to Z, and Z. So that's what we showed. And then, so usual representation is the representation U. G is mapped to G. If you map to like this way, then usual representation, ordinary representation. Representation should satisfy as follows: Ux squared, Uy squared, Ug squared, Ut squared should be 1. And then Ux, Uy should be even. Uy, Ux, and should be even. That should be the rule. That's the ordinary representation. But projective representation is something here, but this is not ordinary representation. In fact, what we saw is that the so for instance, if you look at this one in one half, so that U is X by Z is defined by E to the minus pi I as X by Z. Okay. So then what you get is that the something like you always have this is minus I. What you get is always like this. Okay. So then you can easily see that the Ux squared is equal to what? Minus 1. Okay. So minus 1. Okay. It's not the 1. Minus, you get the minus. And then Ux times Uy is equal to y. So let's do the calculation. So Ux, minus 1 times sigma x, sigma y is equal to 1. This is not a 1, 1. Sorry, which one is I minus I?
Maybe when there's a Q1. Q1.
Is it correct to study?
Minus is on the after up.
Yeah, this is I minus I. And this is, if this is correct, this is equal to minus UC. Is it okay? Does anyone, can you check with the Wikipedia? Is it correct with notation polymetric? Yeah. Is it okay?
Minus is after the right part.
I'm sorry.
In sigma y, yeah, minus sign is on the up. Yeah.
Here?
Yeah. The result is
Oh, okay. Okay. Okay, results are correct. Okay, so I get minus, you have a minus stuff. So usually x, y is equal to z, right? So your ordinary foundation ux, uy should be uz. So you have a minus, negative sign. This is called non-trivial. So this is called non-trivial. This is called non-trivial projective representation. Representation. Precise definition of projective representation. Maybe I can keep now. I think I can do later. I can keep later. Of D2. Okay. So therefore, if you put the e to 2 pi I, e to minus pi I over s x y z becomes usual representation. Usual representation of c2 plus c2 for integer. F is integer for 1, 2, 3. Projective representation for okay, that's okay, that's but from a tilde to a, we use the projective representation C2 plus C2 on this matrix, on this matrix. The consequence is as follows. So what we saw is that the matrix product state is something like A, and then okay, so we go like this. And what we did is that the C2 plus C2 plus C, if you use the element of G. So in this case, I use the G is equal to Z. G equals to Z. And then, but for the other element, it's the same, acts the same way. That X, Y, Z acts the same way. Then we dress with this U. Sorry. Let me write down. That's good. Okay. Okay. And this action is the UG, is projective representation. But here, once you cut, so once you cut this periodic signal, so once you cut here, so if you cut in here, then what you end up with like this one. Like this. So once you cut here, so the U, this non-trivial representation acts on the A, and then they. So the other U cancel each other. The other U cancel each other. So this is A tilde, A tilde, A tilde, A tilde. But once you cut, what's left is U and they cancel each other. So here, so if you look at the open chain, receive. Projective representation. Receives projective representation of E2 cross E2. This is equivalent to you will see the edge. The edge state. So here you have a freedom to act on this projective representation of the D2 cross D2 that flips the edge mode plus minus. So that action will tell you that there is a D2 cross D2 state that appear on the edge of the open. So now we haven't go to the we haven't get to the point of the why it's called the topological. So this projective representation is somehow related to so-called group cohomology. That's I'm going to explain. That's I'm going to explain from now. Okay. Before that, any questions at this moment? Okay. So that's generally consideration to the much more general. So let's consider of G. Okay. Let me rewrite here. So let's consider the MPX length. Okay, MPX length, which is sigma. Sure. And here now sigma is in S state. Well, we can take the following value. And then, so here, much more general, I consider A is T cross B matrix. Now, previously, S is equal to 1. So if you take S equal to 1, and then D equal to 2, we have the balance of solid state. But here we can generalize to this in S and measures equal D. Okay. So then the transformation. So suppose there is action. Sorry. There's another constraint we need to think about. So we impose something called injected. So A is called injected. If sum of sigma and sigma so where lambda is a constant number, and also a sigma and sigma L zero becomes the E by E measures. So that's the injected. So we impose the condition A is injected. Suppose it has a form 2 constants. So that is somehow technical condition to this for this generalization. And then we consider that representation G acts on G goes to G, and then that acts on the D to the S plus 1. So this is a space of sigma. That's the action. So since this action is the so this is in S space is the dimension 2S plus 1. So this D to the 2S plus 1. So therefore it acts on the in S space. Okay. And G acts on this FES. And this can be understood as sum of sigma raised of n sigma in sigma L. And then this can be act as the point time like this. So but sigma prime. Okay. So here I put the identity that the identity is equal to sum of sigma prime, and sigma prime at each side. At each side. Like, at each side. And this can be written like this way. the n tilde sigma prime, it can be written as follows. Of sigma. Okay, so that's what we are defining. Sorry, or okay, sigma prime is something like this. Yeah, like this. So this is kind of technical assumption, which is not important. Assumption. And suppose this MPS is the MPS system is invariant. The system invariant under G action. Then the G action means that you just receive phase. This means that the MPS, if the action just give you the phase to this system. So that in quantum mechanics, always in general quantum mechanics, the system is invariant up to some phase, or states. So then it's invariant. It's just if the action give you just phase times the original state, this means that the system is invariant, or action is invariant. So this means that the so as I mentioned, so this means that if n given sigma is something like e to the I a g divided by L u a u dagger, whichever u dagger. If this is the case, this is satisfied. So as you recall, MPS is different. So for example, so as I mentioned, so this the action of this U G on the MPS is n tilde of this one. So this is exactly equal to the sum. If they satisfy this condition, so this is just a sigma prime, or e to the I a g, and then trace u a dagger u a u dagger u a dagger sigma L, sigma 1, sigma 2, and so on. So therefore, u dagger and u cancel to get this original state times e to the I a or g. Okay. Of course, I don't need this one. Okay. So this one is essentially equal to e to the I a g times n. Therefore, this is sufficient condition to get the okay. And the A tilde is equal to this is the case. Okay. Then you just multiply. So this should be equal to this means is that the A tilde is equal to sum of S sorry. Here like this. Okay. So that okay, that's what you get. And then, so if you perform twice of the G action, so what you get at bottom. Interesting what comes from it. Sorry. So this should be E. Sorry. Sorry. I changed my. So this happened. Yeah. So I just multiply inverse of this matrix with it here, and sum over thing. And then this should be prime. This should be prime. Okay. And then, so what we have is the U H vector, and then U vector G of sigma prime U E. I hope everything's okay. Yeah, I hope it's okay. I just got complete. Okay, I hope. Like this. It becomes like this way. Maybe I will. This one, in fact, can be written as follows: AGL, GH, sum over sigma prime, sigma vector. Yeah, I think I made a mistake. Sorry. Sorry, I think I should write down this G and H and G H and H G and the UGA and sigma prime is cover GH. That's what we do. I'm super sorry about the notation difference. This UG action acts on this sigma. And this U action acts on A. So maybe it's better to distinguish the action metrics. It's better to call, if you call it this U acts on sigma, maybe it's better to call this a P. Sorry about it. I call it, it's better to call, they're not the same metrics, so it should be B and B dagger. And B and B dagger. Sorry about this. So U is the action on sigma in state. B is the matrix that acts on A. Okay. So it's a difference. So sorry about it. Sorry about it. Like this. Sorry about it. So now you can show this so since so they are equal. They are equal. It's usual representation. U is just representation of G. So we assume that U this is the usual representation. So therefore we can show that the so you can show that the usual representation. Yeah, I think I mixed up the notation. I call this U sub G and U sub H. Sorry about it. So this is GH, okay. So this is UGH. Okay. Okay, so then UG, UH should equal to UGH. And also, this the action of this. What I did is the matrix U G of J acts on and times U H acts on J. I hope this is okay. Yeah, I think it's okay. Acts on MPS should be equal to plus UGH acts on J acts on MPS. So that's what I did. So this means that this from here E to E I over L and G plus is equal to E to the I over L and G and H. Fine. So now the consequence of this one is this should equal to this. So BG BH acts on A sigma B dagger H B dagger G should equal to B dagger GH BH. Next step. What I do. Fine. So from here, one can show that the is SC. SC. So that's what we have shown. For instance, if you multiply B daggers into left hand side, and so BG and BH on right hand side, you have a computation ratio. Now, so we use this assumption. So if you multiply, maybe here. So if you multiply this B dagger GH, BG, and the BH, S more 1, S in 2, so S in 0, should be also 0. But we know that this matrix span the D cross D matrix, so therefore this only happens when this matrix is identity times space. BG, BH, BH times B dagger GH is identity times space. So this only happens. This is the diagonal times some constant. Because we already have this standard equals matrix. Okay. So this means that so this is the conjugate. So therefore BG times BH should be equal to E to the pi GH times BGH. So this is what we saw exactly before. So D2 plus D2 case, we saw that the UX, UY is equal to minus UP, right? Here minus sign is the phi is the pi I, pi. Okay. So this means that this representation should be projective representation. Projective representation. Sorry about that. So the here is a bit okay. From projective representation for general G action. From there, so I will explain that how to relate it to so-called group cohomology after the break. Okay. After the break. I think it's better. So let's take a break and then talk about the projective representation a bit more general. Let's. I will explain the rule of the exam after the break.
最后的时候开始讲，这啥人？都是啥找你叫啥人？这些东西都能想到我头里。比如说，投资会走到这个关系。我这个，对，他有一个不能一个两套表，一套就是包这个，还有一套就是这样。你这不是真实的，没信号。 解。我也懂。
So after the break, I will explain the rule of diagram. I will repeat.
因为现在这个问题，因为如果你再有一个定律，动物的一个什么这个什么这个这个因什么一个啊，这个照流法，连续的变上，对，反向，现在这样一个就是沿着一个 x 轴 y 轴这一种转180度，你问你一个提示，就是先绕中总国度转180度，再绕转180度，都是给这回到原来。但如果你先让 x 轴的180度，然后再让 y 轴转180度，它要求就是说，你这样操作跟你直接绕 z 轴转180度一样，你直接绕 z 轴转180度这样转，然后。是这样，它有定的，我们看是咨询过程中的这个六学的分析跟那个对，然后这个本来这个点的是意味的，这里就因为如果没有这个话，最后像有这样一种还可以有区别吗？一起对，确实有有点反对因为这个自学来说，那个对这个对，那个上关上，这就是这个讲也是男的，对。
That's how use action. See action A is projective action. And action is projective. That's the concept of how this action A action
这样按照经常，这样也就是说这个 projective 跟 and， 因为它刚刚讲一个排位就是一排二排啊，然后中间那个
yes，
中间那个
那个 half dimension。
总之上面有一个10负13个值，
就是和情况。对，这个应该和指导线。
上节的讲对不对？上节
一个是 high rotation， high rotation。
如果从正到正还是怎么样？
我们这种就是这个 and projective 最主要是非常
对，
就是3个，
就是
A0负1个个。
反正3个。
No, when you say representation, usually you assume this. So when you say projective representation, you can have a base.
一点出来一点。这个定义为什么一点出来？
就是那个构造法那个，反体字态的那个。
这个是 VBS 太定义里面，对，对 VBS 它不太有在头表会对。上节课上节课，我确实老跟你讲，拆成2个1/2，然后。So 左右两个 side 构造一个系统的这个投影，
It's good.
那是之前的，这个是
This case is satisfied this condition.
要构造这个，反正一个
Definition is this.
是一样。一个给表现的样，一个表现的 listed 的这个一个做 listed 的做这个操作的
sufficient conditions that satisfy this.
OK， 这个是他那个转圈的。
After that, it
是人的算优势
ordinary.
对，他就是还有第二种这个第二个。
Okay. So from here, this is what this means.
怎么样？哦。
I just multiply because inverse length.
这样。
And here I multiply twice. Yeah. So this is
啊，那这个是直接到这边变这个系数。
对。
那这个求和 C 的嘛，
就把这个东西放，这个本来是 VSD 所有的地摆在这边 ，this one is equal， 然后你把这个东西算对的。
this
这里是不是就应该是
and it should be representation.
这语逼是不是就
然
这语逼的定义就是这个，语逼是可以从就是你这个把 A 一变
对，把 A 变成 A 方 Y 的这个一个对，从这开始读。啊，这是你之前那个单个是对的形式。
This part will be equal to
那它不是负一的 sigma 是刚好这个 A 的一个 sigma。
发送吗？
哎，这个零是这个，就它是一个一种，它并不是零是吗？
对对，我就是说，所以这个 sigma 是一的 sigma 是3。
this part will be equal to
这个 A 0这个 sigma 从 A 可管了，所以它直接得到一个，然后说这个 C， 我不太懂这个 sigma 是啥。
哎妈呀！这挺好，我在这上面有 A 是，
这个 A
就是那个 matrix， 就是那个
就是
一个 VPS 送的那一个节点给它变成下一个。
是的，是的。也可以就是它这个节点就这个，
反正根据这个定义去把它。哦，反正知道了就。
You create a link to have two operations in the group in the page. As
你说这个 sigma 是怎么去？
G and H is that establish that it is the every
simultaneously.
So this
然后后来他又写了数据分为
so 它有两种这个做法，也仍然可以做成两种表象，一种表就是这种正常的，一种表是这种索引表情方式，应该是两种。
反正两种像。
是
So here, found D by T 没有，
说到我们课就是他大部分讲内容。
commute
的表示你的表示是什么？
D by T 它
一套叫高对表表这个东西就是它不管用，因为我们现在研究的是在所以，但就是我们希望说定义我们找到这个东西跟那个自觉有相似的行为，所以它就引出这样叫做 projective 的影响。你看这个东西，这种表就跟自觉的表现非常类似，所以后面又全这个。
所以他写了这么一大堆的意思是我们现在研究的都不满这个。
对这个东西确实一样，对，所以我们会用作这样有 projective 的影响。然后接下来就是电力的对吧？然后再就是他说你工作的都是那要看数学嘛，这个是整是后来是那个反正这个就是反正就是说就是说的那个你选的表示得跟你自选的行为是相同的。然后接下来就是说，他研究这个就会更加，就这边就研究一个矩形整体，而且这个超级一个任意的积，对，然后现在就任意一个数嘛，然后他就研究这里开始干嘛，然后这是这个，
到后面就已经是任何一个
对，这我知道，对，这后面就已经讲任意 OK， 然后接下来 这就是这个抛值，就是x等于这个就是就是全称的表示，这是一个这是一个
复数，一个维度是 2x 加1的复数。
就表示它是一个从群中元素到一个线性变换的映射。它这个线性变换指的是它是一个2x 加1维的一个不矢量上的一个线性变换，它是自己到自己。所以它是一个群中元素到一个映射的映射。也就是说，这个是一个群中变化，对，它是一个群中元素到一个线性变化的一个映射。然后它这个，然后接下来就是它跟前面就是一样的操作，就是这边就是都跟前面一样，然后然后其实这点过来的不是
这个是用了那个 identity。
所以并不是个
不是。这个东西不是PS 是这个东西。它作用了一个这个东西，多了一个这个，又多出来一个这个东西 I， 待会儿
它这个乘可以是，它会乘两边上。最高是就它乘两边，书包。然后比如说这块，然后再乘一个这个2，这个明显就，然后是它这个必等这个，这行。我怀疑这个是这个东西，这样当然等于没这好。如果它等的话，我确实对。对，比如说就让它省，很少看见这个吃还是对的。
因为它是直的。
OK， 这个，好，再把这个换。
换 GF。
不是任意的意思，就是你这个题在你这个群的操作下是属于这个
作用。
就你可以让太作为一个瞎子。
那俩 F 就玩这个自动量都干嘛？
操作的时候一样的。我看这个是。然后这个不让。概率然后就是说这个体系在这个它是写那个在那个上分是那个解不变的，说白了它就只能差这样一个相位。它是这个然后这里就是其实就是这句话的意思。然后现在然后这里是在就是这里嘛，这里呢就是把这个直接给写开了，这个在这里说一句，再说一句。然后它这里它当时引入一个，就是先引入了这样一个变换嘛，然后这里它可以对，就是因为这个就是说它是受在这个它的这个是不变的，然后它后面接的是这样，就接了一个这个它的定义，后面这个变换的定义，接着然后我这个是能这个也是过强，把这个成功，这好像是做这个图，做看，对，这边是做的图，相当于就把这个 AC 码写出来，是它定字，这边从它送的图，
For instance, trade
对这儿
metrics like this or EU, then just translation function.
这个呢，这个然后这个就是
So translate periodic.
这个变化是一个定义，这个来应该是然后对，这个是这一步，就是因为它是它假设说这个题跟这个下面是不变的，然后它就开来的，然后接下来就用这个高飞就这个。对，然后现在就推出这个等号，然后它现在这一步就相当于它取了两个群里面的操作，对应了对应的 H，然后前面这个等号是把对应的 H 分别就是分别对在这个上面，然后这个下面是把它一起弄在下面，这推出这个相当于还是刚对，只是说是把这个分两条，对，然后就是把它看成同一个操作去做，然后就有这样的对关系，然后这个我就是这个到这个就差别差一点，这个。还有风险。
你把这个东西给它拿过来，就变成就是单的，然后你把这两个东西拖过去，然后带着这个，所以就发生两个对应了。
然后完了这个后面就对关系的。
Okay. Shall we begin? Okay, again, let me. The rule of five. So I heard there are two rules, one for undergrad, the other for grad, I guess. Next room, I don't know. I think that's the case because yeah. The final exam essentially comes from the content of the lecture, many derivation, whatever, also some conceptual question. Um, the rule is the yeah. So book is okay. Book also print copy, iPad or tablet without keyboard. This is the most important. So this is the condition, but no laptop. Laptop is not allowed because you can hide. But iPad and tablet, no internet. So we will check all the so one by one students before the exam. So you should come earlier, and I will check no internet, and also you cannot type. No, like no pencil. I have pencil. Only no typing. So use only PDF reader. Use only PDF reader. So that's the rule. So one student asked, so you don't have iPad or tablet. I have one, so I can borrow you. So just send me a PDF file you want to read. That's okay. I hope not so many students do not have the iPad. I think hopefully people have. I mean, I hope many people have this. So nowadays Chinese students are rich enough to have this channel. Right? So hopefully this is okay. Hopefully this is okay. So I can borrow it. Lend you. I can lend you. I have a one on my own phone. Okay. So that's the rule. Any other questions about so? Yeah. So if there's no internet, you cannot use any whatever searching and AI and focus. Okay. So that's a rule. There are not all students that can hear, so please tell your friends about this rule. Maybe I should send this one to the WeChat group or e-learning. Yeah. So we will check. So we will check all iPads with no. Like you should. I want to check. Like our TA will check. You did turn off the internet, so therefore come a bit earlier. Come earlier. Because there are 120 students in total, so we need to check everybody. I mean, yes. So the reason why I allow the iPad tablets, if you don't allow some people like copy 200 pages of my lecture notes or something like that, but I really want to avoid. It's a waste of paper. So I mean, just that's it. Any question about the final example. Okay. So, and the final example counts 50% of your score. And 50% comes from half, the other half comes from all of them, right? Okay, so that's a board. It's boring one. So, boring part of the lecture. So the people ask, what we are doing here is that what I'm doing here is that here is the action of reading upper one. So UG and then UL, so UH act independent of this MPS. The upper one is upper one. On the other hand, the lower one is the UGH. So since G and H, so this action is a representation. If you GH acts simultaneously on MPS, you get the lower one. And I compare just this one, this part, and this part, and then the power chord will give you this computational relation with A. Computational relation with A. And if you use the injective condition for A, what you end up with is the problem, which is for projective representation. So now let's take a look at the meaning of this projective representation. So, if you look at this one, so what we want in BG, BH, so that's what I want. So this is equal to, left hand side this one is equal to B, GH. Times, oh sorry, HL. Times G. And this is equal to like this. So the phase factor is like this, become like this. On the other hand, if you do this one, this is equal to e to the I by like this one. Like this one. So this means that the phi GH plus phi GHL is equal to like this. Multiply. So this is called simple type of condition. So this is for two cotype condition. This is for two cotype condition. So here, people just often write down the notation is like this. Right? People just say that D2 G U1. U1 means that it takes the value of U1, right? So it's mod 2 pi. G is the original source. And then so if you change the base of for new representation, it's just you change the base phi of G. So if you consider new representation, just only change the base of representation, projective representation. Then what we found is that the following. So BG, BH satisfy. B prime, G, B prime. Like this way. And then you just plug this one into here, what you end up with the following. This is equal to e to the pi phi of G plus phi of H, G, H equal to okay. So it's really a boring thing we are doing. Then when number is this phi prime of new phase is a previous phase minus psi GH and plus psi G psi H plus or G. And what we want is that we want to identify this phi prime because we just change the base of the projective representation. So this will give you some equivalence relation. So if they are related by this relation, this means phi prime and then phi are equivalent. We consider. Then H2 of G of U1 is so this whole cycle divided by this equivalent relation. So this is called second degree cohomology. And in fact, so this what we saw again this matrix product state coming from BBS state, so AKLP BBS state is sum of n-1 okay. And if you act yeah, so I think it's better to balance bond state like this way. So you assign it N here and N here. what I'm doing here. So yeah, so okay, so if you go on the open chain and act the U transformation, so that acts on D2 element G, and then D2 plus D2. Then what we saw is U acts on A, and then A, then U. And then at the end, so at H station, you see projective representation of you see so sorry. That's the U or now B, sorry, now B. So now this notation you use B, sorry about it. The notation is the B, which is in fact the group cohomology is H2, Z2 plus Z2, and the U1. In fact, strictly speaking, this is in fact Z2 function because we already saw that this is H2. So Ux, Uy, Bx, and By is equal to minus B. Minus means the non-trivial element in Z2. So coefficient can be Z2 here or homology Z2, but for the sake of simplicity, let's call U1. It's inside of U1 because on the other hand, so trivial Hamiltonian. So we have an over 0, 0, 0 ground state. So this is the ground state or VP X ground state, and this is ground state. It's all 0. 0, 0, 0. So therefore, it acts as trivialist receive. Trivial representation of DQ cross DQ. And this is notion. So in fact, non-trivial. This is non-trivial. Cohomology. And this is the trivial group cohomology. So therefore, looking at how this group cohomology element show up in the H state, you can distinguish one to the other. So this is really topological concept of group cohomology. That's why cohomology, the group cohomology is topological concept. That is called topological. Protected topological concept. Now, this is a bit abstract. This group cohomology is a bit abstract. Let's do the one by one. Cocycle. This cocycle condition. This is cocycle condition. Which looks a bit complicated. But so graphic understanding is something like this. G, H, then L, G, H, L. Maybe I think it's better to call it L and GHL. Or HL, HL, and GH. So that's one way to understand. Bit graphical. Another way to understand is as follows. Suppose, so you know that the So let's count the number. Some number. N, which is 100. So let's suppose, give me some number in this range. 38. Thank you. This is 30 plus 8. Give me some other number. Random number. 53. Wonderful. Okay. So, okay, this is 3 times 10 plus 8 is 5 times 10 times 3. Okay. So if you consider the so-called short exact sequence, this is 10-state relation. This is the first stage. So therefore, 38 is actually 3 times 10. So this is a multiplication by 10. Okay. And then here you just mod. So this is mod 10. Okay, mod 10. So this 3 and this is 8. So this is 3. Okay. And then where is the correction? So 53 is 5, and then and 3. Okay. And here we just want to add them up. So let's add them up. If you add them up, what you get is the 91, if I'm correct. Okay? If you add them up, okay? So the first one is the mod 10, so you get a 1. If you add them up, you get 8. You won't get 91. You need something plus 1 here, right? Okay? Plus 1. In Japanese, so it's in this plus 1 is 38 is 11. Therefore, you need a plus 1. This is for carrying in English. I don't know how they call it in Chinese. How do you call it in Chinese? So in Japanese, it's called like this. Let's go anyway. So what we have is 2 pair of A1 and B1 plus A2 plus B2. Sorry, A2 B2 is in fact A1 plus A3 plus 5 B1 B2. B1 B3. B1 plus B2. That's what we want. 6, 5 is exactly satisfy the two cycle condition. Can you show that? Let's. So to show that we just need to do the same exercise as before. A1 plus B1 plus A2 B2 plus A3 B3. And if you now add this should be equal to A1 B1 plus A2 B2 plus A3 B3. From alpha 1, what we get is A1 plus A2. Lower one, what you get is MP here, but the other piece is different. Like this. Therefore, this part should be equal to this part. So this is the additive version of this. This is multiplicative version. This is the additive version. So therefore, this carrying part, or in Japanese, like it's called Korean, but anyway, satisfy this co-cycle condition. And if you mod up this phase, you get the group cohomology. So that's the, and then in particular, this is for extension of the loop. Extension of loop. D10 by D10. Usually, if you have A, B, D, 0, it should be extended by A. I think that's the usual notation. B extended by A. But not how. It shows exactly as we go. And anyway. So, more precisely, so this shows exactly is the kernel of G should be equal to image of this shows it. Anyway, so that's the, but here, okay. Fine. And in particular, you pick the element given the element say gamma in C, suppose the gamma can be written as the A times gamma G. So this. Sorry. What's the best way to explain that? G is inside a. Sorry. I think I'm doing something stupid. This is B. Can be expressed as A times gamma G, and G is B, and A is And then gamma G and gamma H should be equal to A times GH, and then is equal to gamma GH. So that's helpful. Yeah, so here, this element is inside and then, so express. So then, this element is the fact S should satisfy. Two-cycle condition. By the same reason. And the choice of gamma G is not unique, actually. So the choice of gamma G is not unique. So therefore, one can just redefine gamma tilde G is equal to gamma G times some G. Then it turns out that this A tilde GH should satisfy G, EH, EGH, AGH. Original. So it's just the same computation as I did before over there. So therefore, if you identify A tilde and A, you can obtain. So this is E, G, A, and then it's called H2. Sorry, no, not G. CA, H2, CA. From here, you can get that group cohomology mutual reactor. And so that's how we obtain the usual group cohomology in general. Anyway, so that's so if you just consider the very, very standard notion, what about quantum spin chain and so on, look at the H mode and how the H mode receives the group action and so on of the symmetry, you end up with the notion of the so-called group cohomology. I mean, it's kind of like, it looks very complicated, but from very simple quantum systems, quantum spin system will give rise to this very deep notion of the mathematical notion called group cohomology. Okay, so I think I would like to comment one thing. Before ending. So this notion is this projective representation is somehow related to projective representation of symmetry G is somehow related to so-called anomaly inflow in physics. So we had the following thing. So UG or VG as H e to the I phi VGH like this way. And this can be understood the following. So if you have something like a discrete system, so 1 plus 1 dimensional discrete system is like, for instance, if you have discrete system is like a graph, like I show like this way. So two-dimensional system is triangulated, and they have a G action and H action, and this is so this is 0 plus 1 boundary. So, and if you consider, so you multiply this one. You have a G times H. So here you have G action, H action on the boundary state. So here you have a G, H action on the boundary state. In fact, this action have ambiguity. So this is ambiguity of so inside here is called bulk. People often call this part is called bulk. Bulk. And so this ambiguity is coming from bulk anomaly. Sorry. Coming from bulk as the anomaly small. So the notion we encounter here is really the something called ambiguity, which is called anomaly flow from bulk. I mean, this notion is very, very this notion is very, very advanced one. So it's really like a quantum phenomena, but so it's now vigorously studied even in research or condensed matter physics, and this is related to so-called general symmetry, like many research topics. So group inflow. But I just want to mention, I think it's better not to mention about the detail of the that is way above, way beyond the scope of this lecture. And then this one is called boundary condition. So the H model, so H state will show up a boundary. Is and from other so. So H state and this anomaly flow is flow one-to-one correspondence, and this is called boundary correspondence in condensed matter physics. So this action is really this action is really coming from this the action on the edge mode, and this edge action will give you this ambiguity that is really coming from the bulk gapped edge gapped. Okay. So anyway, so those are named, but so we see one explicit example of this bulk boundary correspondence by using the KLP. So that's the. But here, those notions are like after this 2009, who and when, and all that. That's all. Introduced SPT, it's a really big topic in condensed matter physics, and then just many people study even in currently. That's wanting to show as one of the simplest examples. Okay, I think I just finished what I wanted to help. So thanks for taking my course, and then yeah, so good luck in
大概到第10章才可以看，基本上。我这个大家可以看。
老板做着这个水语义均衡，这怎么样？我能走在几个方面。
Please can finding one you want to read. Yeah, Richard. Then I can.
反正我只要课理解它就是一个平元素到不是
Yes, then I will take from them. If not, then I will send you the.
其实一瞬间可以把你追下去。对，反正几个预期的用可以看。他就是我说你在做加法的时候，对入位的，他进就是你要是进了一位的题啊，我进位就然后就是他就是相对比那个就是那个就那个记不清的时候，还累。So if this is equal to one expansion, all this
That's true.
就是这个就是让我来先对前面两个对这个机概不，就是总期在这个公式，先把第二、第三对，但是你先把 B 跟 B2 加起来，它进一位这个是 ID 第二这个，然后第二次就是 B 第二个。第一家留下来那个个位的那个是第三项，那它你再排列第一个的基本上这样，然后跟下面那个就是先把后面两个相加，再给你定位的就是一样，就是三个数一样的这样子。就是所以相位组，看他那个白药类似这个。我数学记得，但是太记了。操控是这个。
有小号，有小号，有大。那个我那有个号上没我把那个
这个就是所以就是因为自选跟儿童嘛，有我也就是我这个场大一口，
我好像看过这个
他基本上来看，这个办的就是微信群，对，有这片段是这个对，这个然后我刚说那个
微信，我这微信有问题。
不乱记，这个主要是从他们那个相位上。
我想想还不行。
那个不解标的，就是我觉
然后上周过来说说有飞机哦。
这边还有一节上，
没他都不加带，没有别的包。
我们再讲一个情况，
我2008这个2008的
6天前，6天前。定了，对他非常高。对不起，我看过所有群。我们来看趋势。
这一个都收过去。我认识有一个大二把这个学掉了，不知道
晒鸭子掉。我感觉停了，也是一直撞，要改变。我是上海人，我不能讲话。
互联网中国说那不挺好的？
是可以啊，
已经买一个，他把它要停。
我们这个都找点卡，对，那个点卡的，我告诉你，只是说那个几十块钱，对，刚买到，开心点，我就装了4个点，就更能量点卡。我知道，我上网是感觉不能买，之前就是一切的，我之前是可以分的。
现在买了，直接过数。
然后他反正让你做要做所有的选择，自己点不做，提供的在做。没有，当然又说他应该是争取这种复习速度这个玩意，我觉得就是好奇什么，就是你天天都看那东西看。还好他那个时代我一开始大家有去物流就是对于然后你看前面那些看我这2年解决这个，就是复习选这个，2年的复习，我应该等于当红飞的通过这个2比1的这个事情，就是这个
他们有这种那个 H 方
啊对。应该也是个问题。
没有。
应该只有你可以给这个写好，给人写好，那个是我们现在希望你这还知道。右上角第二，U， 那个我也不知道你得到多少长子，我也没记住那个。就一直。那个 H 方还是这样，就一啊，也有像是H 平方对吧？啊？那不是那下面1的那个，就是有1、2个元素，或者说1和负1两个元素。那结果 H2 的这个意思，什么谁懂那个 H2 0是学妹。
Yeah, I think the meaning is that the probability
所以这个 G2 要是表示我不知道这循环群的意思，它个第一个下面是
I think it's
2个2对，那2个都我也没听了不一点都一样，感觉忘了。2是比较强的是
Yeah, I think it's a probability to take the occupation of the you have a bunch of things. And then you want to take then in order to
我还没你懂。
So if there is a high temperature, it can go to very high temperature. It's very from heating, staying one thing is very low. Some of it is
拿一个来交易。不分组织，我自己晚上最多是把2项发给我才看到。周末2天网上2天，大概4、5天在忙的地方，接下来就随便看。不过到他昨天讲那个什么液体嘛，老道，然后类比液体，然后还讲了，然后是然后是超导，然后是卡西。我这刀就是我这刀还有我半导体我必须这一次啊，但半导体它和这对吧？就这些，然后这这个快这个东西就是表示在制作2个时候，一位数型加到手，进位就把就显示到进位就算是然后其他跟2个一在讲。然后就是它可我进来处理一个也可的不进文在也可不进文，然后就是你先一个题把2个一位数算出来，再加另外一个一位数。其实你先把前一个数再加另外一个，这是应该进位的个数次数一样。然后这就其实是所以这个相位也是这样，它也满这样子的。对吧？这样子，上午要别地方，对，或者说其实结合律所要求，一个，对，好像在虚无主义啊，没有就是或者看到没有我用2笔在干，就是我能买那个，这个还只是要证明的，一下这个不是啊，你加plus。那就是理解啊，这个每个区位都管理问题。OK， 从问题给你修。对，它其实隔音还是引入很高，跟我们电动课上讲的都是完全不一样的。我觉得你可以把它比起来，尤其是从普分解那个角度理解，应该是。对，它这个直接告诉我们，就是说你的格林函数这样的一个形式，格林函数没有都一样。但是我这个就是告诉我们，就是因为它是从这个偏微方式当中讲嘛，然后你并不去给你记这个概念，但是就告诉你格林函数形式，然后给你带回去，发现确实你把这边带进确定的方式，右边就是最小的函数。它应该是跟这个一样，有点像和数学方程式对话是啥？越讲历史越他不会绑定那个什么就他告诉我们说有这样一个东西，然后你把它对这个东西，然后你把它这样带进这个确定的方式，发现哎，它确实有这个属性的。然后它这边解完之后也是，然后是不是这一而且它这一项是什么？就是我们上课这个东西，我们上课说为了避开零点，然后为了推理它，但它这边就是直接